Okay, so let's have a look at this problem. So with this we've got an object right up here, able to move around, and it's going to be falling down. But before it falls, it's got mass, it's got gravity acting against it, and it's got height, 5 meters of height in fact. So for this reason it has potential energy, and this was given to it by whatever lifted it up this height. So potential energy, we know, is equal to mgh, which is equal to 15 times gravity 9.81 times height 5 meters. So this is equal to 735.75 joules of energy, capital J because it's the name of a person, all stored in this boulder, ball, whatever it is. And its kinetic energy at this point is going to be equal to half mv squared. Well, it's stationary, so this is going to be half times 15 times 0 squared, which is 0. So it has 0 kinetic energy because it's not moving, and kinetic energy is moving energy. So as the ball falls, eventually it's going to be turning its kinetic energy, so its potential energy, into kinetic energy. As it gets faster and faster, more and more of that potential energy is being converted to kinetic until it reaches the bottom. Now when it reaches the bottom, kinetic energy, again half mv squared. We don't know velocity, it wasn't given to us, but our Suvac equations say that v squared equals u squared plus 2as. Now we could convert this and say v equals the square root of u squared plus 2as, but actually we're going to introduce a rounding error there because our formula k equals half mv squared needs v squared, so why square root it and then square it again? It's just going to introduce a rounding error. So substitute v squared for this, u squared plus 2as will give us the correct answer. So if we do that, that's going to be equal to half mass. We need to actually just write the mass in there, don't we? Half times 15 times an open bracket, substituting what v squared is equal to, which is 0 squared, our initial velocity, plus 2 times acceleration, which is gravity, times our height, s, which is 5. And when we type that into the calculator, we get 735.75 joules. Exactly the same as the potential energy we put in. So we're making assumptions here that there is no wind resistance or anything because all of the potential energy has been converted into kinetic. Now we can actually see how this happens all the way down if we use Excel. So here on Excel I've got all of my heights, so 5 meters all the way down to 0 in increments of 250 mil, and we can put a formula in to work it out. Potential energy, it's equal to m, so it's equal to h1, so we'll use the dollar function. If we can find dollar h $1, and then times gravity, which is h2, so $h$2, and then times the height, which is this cell here, A, and it gives us 735.75 like we expected. We can put the equation of kinetic energy, which is using part of our Suvac, so it's going to equal 0.5 times mass, which is going to be $H $1, lock it to that cell, times and now we're going to do some brackets here, U squared, which is always 0 because 0 squared is 0, plus, need to open some more brackets now, 2 AS. So in this case 2 times $H 2, oops, need another dollar there, times, and now it's how far it's fell is what its velocity is going to be related to. So that is going to be equal to 5, because initially it was at 5, take away what distance is it now, so where's subtract gone, take away whatever the distance is now, and close those brackets up, 0. We'd expect it to have a 0 velocity at the beginning, sorry, 0 kinetic energy at the beginning, but now if we fill down, we see there at the end we get 0 potential energy because but it drops gradually as it goes down, we get less and less potential energy because we're getting nearer the ground. If we do the same thing with the kinetic energy, gradually as we go down we get more and more kinetic energy, as we see here, as it goes to it, and less potential energy. And if we looked at the total, we could add these two together. So equals that, add that. So add the potential to the kinetic together, and they come to 735. But if I was to fill that down and do the calcs all the way down, they're 735 all the way. It never ever loses any energy. The potential energy and kinetic energy always add up to 735. So no energy is lost there. So the question is then, kinetic energy isn't lost. When this ball bounces back up here to, let's just say, 4 meters, then its potential energy now is mgh, which is 15 times 9.81 times height, 4 meters, which is going to be equal to 588.6 joules. So clearly energy now, it isn't adding up to 735. Some of that energy must have been lost, and if we want to see how much, energy lost is equal to 735.75 take away 588.6 equals 147.15 joules. That is the energy that we can't account for. It's gone somewhere. So if it didn't go when it was falling, because we didn't take account of air resistance, it must have been transferred at some point on this impact. Now, as we looked in class, when we see impacts, what happens is it tends to leave a heat mark behind, just the compression of the particles, and the actual object itself will have changed its internal temperature slightly, because of the compression of the particles together, the friction. So thermal energy is one way it would have been lost. Another way it could have been lost, or energy transferred, is through sound waves. So as we see things impact, sound waves are given off. That's a percussive movement of air particles, and that emits and travels out, but it's energy being lost. So various other different ways, and we can't quantify them in this experiment because we're not given enough information, but we know potential areas where energy could have been transferred into, and as part of your write-up for an assignment, you might want to discuss those potential areas on this impact where those could have gone.